Go through what I've been doing with this invaders idea. It's sort of abusing the tile maps, but in an interesting way. So I thought it might be useful to. I'll share the code at some point, but I just want to go through what it's doing so you can see. It's also an interesting. It's turned out to be an interesting exercise in how to efficiently use. Well, not efficiently, but effectively, maybe, to use subgraphs. So it might give some ideas about why subgraphs are so useful. So I'll just show you what it does first of all. It's not a full game by any stretch of the imagination. I'm just working on the bits and pieces at the moment. So what I've been working on now is to get the rank of invaders to be configurable, so I can turn them on and off as they get destroyed. So what I've got it doing now is it will start up randomly, setting a random set of invaders in the rank as already killed. So each time you start it, it starts with a bunch of different ones already killed. So everything else still works. But you can see it kills off a bunch of them at the start, and it's random each time. So it's just randomly setting it. So I can show you what that does. So the way that I've done the is dead or is not dead is unfortunately a bit cumbersome at the moment, because we don't have arrays, and I'm thinking this is sort of getting me more towards the idea that getting some sort of array support in there would be useful. But what I've done is in the global data I've defined these 5 variables, rows 0 through 4, so that's for each row of the rank. Now there's 11 invaders in each row, so each one of these is a 16-bit value, so I'm just using 1 bit for each invader. If it's 1, it's dead. If it's 0, it's still active. So what I've had to do is some nasty code in a shared logic. I put a bunch of shared logics, subgraphs in here that I use in various places. This is the nasty one because this basically has to get the right variable for the row and then work out which index on that row we're looking at, and then do a bitwise and on the value to get it back out. So I'll just quickly go through what it does. So it takes in a cursor. There's a cursor. The idea is as you're updating the rank, you update one alien at a time. That's how the real invaders does it. So you update one, then you move on to the next one, then the next one, then the next one, then you go up a row and you move on to the next one, and so on. So this cursor just increments each frame through, and that's why you get that unusual characteristic, that the update pattern that you see in invaders where it moves one at a time is because of this logic. So the cursor is just an index 0 to 54, because there's 5 rows of 11 invaders, and all it's doing is it's first of all checking if it's out of range. So if it's 0, if it's -1, and I'll explain why in a second, it just returns it's not visible. Otherwise, it first of all divides by 11 to get the row number, and then uses a new node which you guys won't have access to just yet, but it's modulo, which is a remainder effectively. So this gets you, if you do the modulo of 11 and the cursor, you get the index in the row. So these are the 2 values. I'm storing them because I'm using them all over the place, and it's more efficient to do that. And then you've got this nested set of ifs. So this is basically if it's row 0, if it's row 1, 2, 3 or 4. And all it's doing is if it's row 0, it's getting the global variable row 0 and putting it into a temporary place. If it's 1, it gets row 1, puts it into that same temporary place, 2, and so on and so forth. And then each one of those, when they've completed, converge on this single output, and this single output just gets the temporary variable here. Where are we? Yeah. Yeah, it gets the modulo, which is the index in the row, and looks up a bit mask in this select. So it's bit 1, 2, 3, 4. This is the hex value, or the binary values for those bit masks up to 1024 for bit 11. And then it gets in the temp variable, which has been filled in with the data from row 1, 2, 3 or 4, 0, 1, 2, 3 or 4, and then does an ampersand, or an and, effectively a bitwise and of this mask with that. And if it's a 1, it's dead. So because the subgraph is invader visible, we just do a logical not on that, so that if it's 1, which means it's dead, we want to actually return 0 because it's not visible, so, and vice versa. So then that just outputs that. So this is using a bunch of things. It's using the select quite effectively. It's using the merging of flows, so it all goes through this single flow which reads the value out. It's a bit heavy-handed, and unfortunately it has resulted in, on the spectrum, it actually being slower to look up whether an invader is visible or not than it is to draw an invader. So that needs to be addressed, but it works. So quickly look at the other subgraphs we've got. So we've got draw invader, which is really simple. So actually let's go back to this one first, because this is the basis of it. So this basically takes in a cursor and a rank position, so the rank moves, the whole rank moves as an index. That's again directly from the original invaders. So every time all members of the current rank have done their shift, it moves the whole rank across 1 pixel until it hits a certain point, and then it moves the whole rank down 8 pixels and starts going back in the other direction. So we're passing in the current rank, X and Y, and the cursor, and then using this it just outputs a pixel position for the X and a tiled row for the Y, and that just avoids having to do conversions on that because it's always going to be on a particular tile row. That's a decision I've made. So that's just a very simple one. It's used in various places to convert a cursor and a rank position into an X and Y position. So the draw invader uses that. First thing it does is call get invader position with the cursor and the rank data that's passed into this one, and then it will call 2 modified tiles, because each invader is 2 tiles wide at the moment. And if we just quickly go to the rooms, I'll show you what they look like. So these are the tiles I've defined. So it's basically each pair of tiles is the invader shifted across 1 pixel. So we have I think it's 8 frames, 16 tiles to move from there to there in pairs. So what this does is it works out, first of all it converts the X, which as I said is in pixel coordinates, into tile coordinates for use in the modified tiles, and then it takes that same X and works out which pixel within the tile we're on, depending on how. So if for example the X value that came out was 4, then it would be tile 0 offset 4, so it would use the 8 and 9 tiles, which would be sort of here, somewhere like here. So you can see it shifts them across. So that's just working out which tile index, and then it draws that tile, ignoring everything else, at the correct position, adds 1 to the tile index to get the second half of the pairing, and draws that at the position X plus 1 and the same Y. So that's fairly simple. The cost here is these two are fairly expensive when you're doing just one tile, so I might introduce a simpler version of modified tiles which just lets you change a single tile, which might be a little bit quicker, but I'll look into that. The erase invader is necessary because as you shift the invaders across and they move from one pair, so if they move from 0 and 1 to 1 and 2, if you don't erase what was behind them, it leaves a pixel row or a pixel column in the previous cell. So every time you move an alien, an invader, it has to erase what was there before and then draw the new one, just to make sure that it cleans up behind itself. So again, this is just using the get invader position, so it's getting all the information back in, the same information, cursor, rank X and ranks Y, and then it's just converting the X to tiles for use by these two modified tiles, and in all other respects exactly the same, except all it does is delete the tile rather than set a particular tile. So that's a simple one, and then we've gone through the invader invisible. So those are the subroutines that we've got access to. So if I go to the room now, so this is the logic on the room. So we've got a bunch of variables on here, rank X and Y, the current cursor, direction -1 or 1 depending on whether you're going left or right, the previous rank X and Y, which I'll get into why that's important, and the frame for animation. So every time you complete a move of an entire rank, it cycles the frame between 0 and 1. So you get the alien invade the enemy animation going on. So the first thing it does is it does this in a bunch of always, although they look fairly complex, they're actually reasonably simple, always triggers. The first one advances the cursor. So the cursor is, if we go to the game, it sets the cursor to -1 to start with, and that's the logic I was saying about the checking out of range. So the first thing it does to avoid calling is shader visible, which we know is expensive, twice, once when you're drawing and once when you're advancing. I just set it to -1 so that it'll always advance past that one to the first invader. So the first thing it does is it sets a valid. This is using the while loop. So you can see here we've got this while loop. So it sets this variable valid, which is just a temporary storage, to 1, which means it is valid, and the loop will execute on the first time round. Then it increments the cursor and makes sure that it wraps around at 54. If it gets to 0, it sets the move rank variable, which is another variable here, which is used later on. I'll explain that in a second. And then it checks to see whether in the new position of the cursor, whether the invader is visible or not. And if it's again, we're inverting the value out of here because we want to know whether it's dead. Because in this case, what we want to do is we want the valid, which is the control variable for the loop, to be 1 if we want to go round again. So that means if the invader is not visible, like it's dead, carry on and increase the cursor again, so you skip over that invader. This is, as a slight aside, this is how the animation or the gameplay in the original Invaders gets faster and faster, because it will update 1 alien per 50th of a second on the hardware. But if you've only got 20 aliens or 20 enemies on screen, everything moves much faster because it does it in 20 frames. Whereas if you've got the full rank, it does it in 55 frames, which is just over a second. So the natural consequence of the way this works in the original Invaders code is that things speed up automatically without having to do any extra work. It's quite clever. So this will loop around here until it comes across a visible invader, and then it exits, because there's no exit after the loop. So once it hits an invader that is visible, it will exit out, and the cursor will be set to that invader. So then the next time round, the next thing it does in this frame, order 1, is erase the current invader's previous position, and it does that by using the previous rank and previous rank X and Y. That's why I have these as separate things. That's because if the previous position of the invader was on the row above, for example, if you've moved it down, if the rank has moved down an entire row in the interim, you need to make sure that you erase the invader in that row. Otherwise, you end up with these sticky invaders that hang around. So we use that, and we erase it, and then we use the current cursor and the current rank Y, but we're adding 1 to the rank X, because the rank is at a certain position, but we're moving this particular invader forward 1 during this move. So we just add 1 to it and then call draw invader, and that will move that one forward 1 pixel, just that one invader. And then you remember up here when we were doing this update of the cursor, if the cursor was 0, we'd set move rank to 1. So that's what's happening down here, is it's checking after doing all of that, was move rank set, i.e. did we reach the end of the full rank, and we need to did we reach the last invader in the rank that needed to move forward for this particular sequence. And then we need to move the rank, so we'll move the rank across 1 pixel, check to see if it's reached the edge of the screen. If it has, move the whole rank down 8 pixels and change direction. So that's basically what this is doing. And at the same time, it's storing the previous rank position so that the erase works properly. So that's all that's doing. It's just basically checking to see if it's out of range to the right, if the rank position is beyond 48, which is where I've set it as the limit, and if it is, it will change the direction and move down by 1 row. If it's not, it'll check to see if it's less than 8, which I've decided is the position to move down on the left hand side of the screen, in which case it will just increase rank by 1 again and change the direction to 1, so changing back to going right. That's basically it. This is a little bit extra in here. I'm just testing something. I'll show you in a second. This is something I'm testing to see about how I might handle the explosion. So I decided the best way to do that, to avoid overcomplicating it any more than it already is, is to use an object. So I've got an object for the explosion, which I can blat over the top of an empty alien, and it can just sit around for a little while, because in the original game the invader explosion hangs around for about 5-6 frames and then disappears, and leaving the space behind. So if I show you, I've put a quick test in the game logic. If the if the up button is pressed, it kills alien invader number 8. Just as a quick test. It doesn't kill it, but it basically puts the explosion there. So if I run, I think that's okay. So if I do Q, you can see it puts the explosion there. It doesn't kill it yet, but that's how it's going to work. So that's basically what it's doing. I'll share it if anyone's interested. I've got a lot more work to do, and I might make some changes to the spectrum, as I say, to support it. But it does work on the spectrum, just a little slow.